So, a short overview of today's webinar. What are we going to talk about? First of all, I'm going to give a quick overview of the Flexi-Sync project. Then we're going to zoom in on Austria, especially at the pilot site in Maria Laach. We're going to discuss what goals we have in this project and the use cases. And then we'll get around to our methods of implementation and also the results. The Flexi-Sync project is a multinational project. As many of you are aware, decarbonization is a very major process that is still ongoing right now, and this is going to probably lead to a big increase in renewable and energy production. And as we all know, these new renewable energy sources are much more volatile than traditional means of energy production. For instance, in Austria, there is a specific use case for balancing the grid, which is that about 2,400 biomass-fueled district heating systems are present in Austria, especially in the countryside, and many of those are about to reach the end of their life cycle. And in this project, we are going to implement new strategies for renewing those components. And one of the major goals of this is to add stability to the grid. And we are going to do this by utilizing and looking at two forms of new flexibilities, which will be here mainly the CHP plant and the introduction of a heat pump. The overarching goals of these new systems is to strengthen the local energy systems by possibly reducing grid imbalances locally and not nationally. And we also take a special respect to the local communities, because what they oftentimes want to know is how high is the economic potential for the community themselves, and is it even necessary or financially viable to invest in these new technologies. District heating has a rich history in Austria. For the last 70 years, the district heating system has been constantly evolving, and now over 400,000 apartments in, for instance, Vienna are being supplied by the district heating system. And all in all, about 25% of all apartments in Austria are currently supplied by the district heating system. And this has also a major factor in this is the big rise in the use of biomass in the last couple of years. You can see here the statistic ends at 2015, but the biomass use has increased still up to this day. This is especially true for the pilot site in Maria Laach. Why have we chosen Maria Laach as our pilot site? The network structure there can be very representative of many other district heating networks in Austria. Another thing is that most of the components there are not the newest, meaning that it can be possible to introduce new flexibilities, the ones we talked about, mainly the CHP plant and the heat pump. The benefits of those flexibilities is that in the case of the CHP plant, not only does it produce thermal power, by the way, CHP for unaware ones means a combined heat and power plant. That means that it can produce thermal energy as well as electricity. On the other hand, the heat pump consumes electric energy and also produces thermal energy, which means that in the case of a high renewable supply, the heat pump can be added to the energy mix. And in case of a very low energy supply from renewable sources, the CHP can be additionally used to supply the grid locally and not nationally. Also, it's very important in everything we do at the pilot site that there is absolutely no disadvantage to the customers, and they practically don't even feel the addition of these new systems. So how is the status quo at the pilot site? Currently, there are about 35 total objects. So it's a very small community with a total overall heat demand of about 2,000 megawatt hours per year. There are some major heat consumers like restaurants and public buildings and so on, but most of them are smaller heat consumers in the range of smaller than 100 megawatt hours per year of heat demand. So this is an ideal testing site for a small scale implementation of our optimization methods. In detail, what is currently present are 2 biomass boilers, and there's also a small buffer storage tank. The district heating grid is intact, so there is nothing to be done there. And it is not fully optimized yet, but there is a SCADA system in place which aims to efficiently use the regionally sourced biomass. And here you can see the small system in a little diagram. The overreaching goals of the pilot site is, in the first place, to gauge the economic potential of introducing these new flexibilities, ergo the CHP and the heat pump. We're going to test not only the introduction of these technologies, but also we try to simulate the participation of these new technologies on different markets. Those will be the day-ahead market, where the CHP can sell its power and the heat pump can buy its power. Also, we are going to look at the balancing market. We can offer certain 4-hour products, meaning that we can, for instance, offer positive balancing energy, meaning supplying energy to the grid using the CHP, and also negative balancing energy, meaning consuming energy from the grid in case of a very high supply. In the end, we are going to look at participating in the day-ahead and balancing market simultaneously. The reason for that was that the balancing market, especially in the old market design that we are currently still in, meaning the 4-hour products, can be a bit restrictive to plants that generate heat. What we are also going to look at in each use case is the use of flexible buildings. This mainly means that we are going to shift the demand load profile of the buildings, and the goal of this is to overall prevent heat demand peaks. For this special pilot site, this is not that important because the system is already very flexible, but this is not the case for all pilot sites that we can potentially look at. So there are some pilot sites that do not have that of an abundance of heat generation. And for those pilot sites, load shifting might be a very important tool to reduce or to increase the efficiency of the standing systems. We did represent the model, the whole system in optimization model. What we used was a mixed integer linear programming model. We used the Payomo framework because it has a very convenient block architecture, which is very suitable for our use case. We also use the solver by IBM, which greatly helps the solution time for all the simulations. We have 3 main modules in our optimization. The first one are the generators. That means all the technical components. The second one is a special model designed to represent flexible buildings, so that we can not only represent unflexible buildings, but also model the shifting of the loads between time steps. And the third module are the different electricity markets. For the whole simulation, we used operational costs for the year 2010. This also includes data such as call probabilities for balancing data, balancing prices for positive and negative energy, and of course also day-ahead market historical prices. As you can guess, the whole optimization model is going to be quite large. Mainly it's a very large time frame. And the complexity is also quite high. One commonly used solution here is the rolling horizon approach, which is an iterative approach, meaning that you do not optimize the whole year at once, but do it 1 day at a time, always optimizing 2 days in a row, and then discarding the second day. The first day of the optimization is then aggregated together, and this will give us our final result. The generator model itself consists of 3 modeling components. The first one is the CHP, the second one the heat pump, and the third one are the already pre-installed heat-only boilers. The CHP and the heat pump are modeled as being binary modules, and only the heat-only boilers can be modularly controlled, meaning that there is the power can go from 120 kilowatts to 400 kilowatts of thermal power. And this is also important because the higher the power output, the better the efficiency becomes. So this would be an ideal use case for the flexible buildings, because we can reduce peak loads and therefore minimizing the amount of time the second boiler has to be used. In order to compare the two modules, the CHP and the heat pump, we assumed that both have a thermal power output of around 100 kilowatts. Of course, the CHP can only offer positive balancing energy, and it's also important to note that we decided to only simulate the secondary regulatory reserve. The reason for that is that the auxiliary and that the manual frequency restoration reserve, the first one, is far too quick acting for our components. It wouldn't be possible. And on the other hand, the tertiary regulatory reserve is way too unpredictable, and the probabilities of a call are way too low to really be accurately represented in the model. Also, for the whole optimization model, we used a constant biomass price of 20 to 30 euros per megawatt hour. There is not much to say about the storage model. It's a very straightforward, simple capacity model. There is a small, we have an 8 cubic meter tank volume and a small capacity. The other thing is that the flexible buildings can also act as additional storage units, and therefore further increase the amount of flexibility that we have present in the system. One we can say problem we ran into also doing other simulations on other district heating systems, especially on the countryside, is the non-availability of demand data. So what we really needed, also if we want to expand our products to other pilot sites, was a model that can deal with a very simple overall demand profile. And what is really missing here in the missing data is that we cannot accurately represent the demand response of the different buildings, because we don't have the wall parameters, and not really the environmental parameters. That means that what we did here was to approximate this demand response by limiting the amount of energy that can be shifted from one time step to the next. What you can see in the graphics on the right is at the time step of t, we try to shift a certain amount of demand to other time steps, and the amount of energy that can be shifted between the time steps is follows an exponential decrease. That means, as you can see in the two example formulas here, that the total shiftable load is connected to the historical demand profile and also the exponential decrease factor. And as always, the equilibrium has, of course, to be maintained, and also over all time steps, the demand, of course, has to look the same. With this system, we can reduce peak loads, and the main use for this, as I already said, was to limit the use of the second boiler, thus allowing the first boiler to operate with ideal efficiency. The third module is the market model. The day-ahead model is just represented as a very basic cost function. The balancing market is a bit more tricky to really model, mainly because of the pure statistical chance of the balancing calls. Also, we are using the currently active market model, which is that balancing energy can only be offered and bought in 4-hour product blocks. The big problem with this market design, and this is also the reason why it's probably going to be changed, is that, for instance, if the CHP offers positive balancing energy in any given 4-hour block, it cannot really produce any thermal power or electricity. That means that it will lie dormant, and the probability of the balancing offers to be more profitable than just using the CHP conventionally here is quite low. The call probabilities itself are based on statistics, and the total revenues, if you're offering balancing power to the market, are just the sum over the power price times the offered power, then the statistical call probability and the energy that is called statistically times the energy price. And in the case of positive balancing energy, you don't really pay any grid tariffs, which is very good. In the case of negative energy, yes, you get very cheap energy, but you have to pay a bit of a reduced grid tariff. It's not as large as the day-ahead tariff, but it is still there. Keeping all this in mind and based on our optimization framework, the evaluation of the results is always in comparison to the base case. The base case represents the unmodified generator system consisting of the two heat-only boilers. All the use cases are being simulated for flexible as well as unflexible buildings. In this presentation, I rounded the results just so that it's better readable. It doesn't make that much of a difference. And as I said, all historical data is from the year 2010. And on the left, you can see the dynamic price structure of the day-ahead market, which can be good and bad. In our case, what we are doing is an estimate of the economic potential. And this means that we are using perfect foresight, we're using ideal conditions, so that we can get an upper bound of what would be theoretically possible if introducing these new flexibilities, if everything went perfect. And here on the right, you can see a typical demand profile of a small town over the year of 2018. In the base case, it's mainly there to represent the current operational costs, which are about 65,000 euros in the year 2018 in order to meet the heat demand of the entire town. What's interesting here is if you introduce flexible buildings into the system, the costs are not really reduced, so they're only slightly reduced by 1%. And by analyzing the whole system, we can probably say that the system is already too flexible, because the flexible buildings are only useful for peak shaving, and peak shaving is only then really useful if generation itself, so heat generation itself, is already the bottleneck, which is not the case here. So throughout all the use cases, you can see no real correlation between flexible buildings and a major cost reduction. One thing that can be said is that the 1% in cost reduction with flexible buildings comes mainly from the reduction in startup costs, mainly the startup costs of the second boiler, and also because the first heat-only boiler can operate at maximum efficiency most of the time, which you can also see here in the load duration curve. In blue, you have the first heat-only boiler, which wants to operate at maximum capacity up until a certain demand is met. And if the demand is any higher, only then the second heat-only boiler is used, which can be very useful for other pilot sites. If we introduce the new hypothetical components like the CHP and the heat pump, we are also going to try to market the electricity on the day-ahead market. The CHP is usually preferred by the optimization over the HOBs, but this is only the case if the electricity price is higher than 126% of the biomass price. But otherwise, the CHP would be constantly running the whole year round and would lead to a potential cost reduction by 13%, meaning that from 65,000, you are going down to about 56,000 euros per year. In the case of the heat pump, it's even more significant, of course, under ideal conditions, where we can see a potential cost reduction of about 41% down to 38,000 euros. And also here, the only exception where the heat pump is not running is when the dynamic market prices that you can see here get higher than the biomass price for the heat-only boilers. The balancing market was especially interesting to see. Fortunately, if you can say that, the balancing market does not really seem to be viable or not as viable as the day-ahead use case, especially for the CHP. The CHP lays dormant for most of the time. The cost reduction which stems from the offer of the power and also from the very sporadic, statistically modeled balancing calls amounts to only 1.1% in relation to the base case. And also offering balancing energy with the CHP would mean that it's only active 100 hour full load hours out of the whole year, which is, in our opinion, in this use case, a bit of a waste of a component. In the case of the heat pump, it's much more possible because the heat pump only can offer negative balancing power, which has been a bit more frequently called in the year of 2018. It can be active for about 500 hours for the whole year of 2018. And this is a bit of a better result than the CHP, but still not as good as just buying and making use of the dynamic day-ahead market prices. In the third use case, we can see how the system responds if both markets can be traded at the same time. Of course, the cost reduction must be at least as low as the pure day-ahead use case, which is the case. In the CHP case, the additional balancing revenues at the best prices account for about 0.7% of additional cost reduction, and for the heat pump it accounts for about 0.8% in additional cost reduction. So this use case would be at least much better suited than offering balancing power alone, usually. So what are the conclusions? What are the key points from our findings of the simulation? First of all, flexible buildings, the flexibility that is present in the buildings only then makes sense if the system itself is not already very flexible, meaning that the generation of the heat is a bottleneck. Only then can we see the real benefit of flexible buildings. In the test site of Maria Laach, flexible buildings only provide potentially a very minor cost benefit to the whole system. Also, offering balancing energy alone is oftentimes too restricting for the new components that work at their full potential. Instead, a potentially very lucrative use case, especially in combination with the heat-only boilers, is making use of the day-ahead market access and trading the power directly over the day-ahead market, selling the CHP power and buying the power for the heat pump. In the next steps, one of the next steps is the implementation of the optimization framework at the pilot site in Maria Laach, which will probably start at around February next year. And what we are going to do then is to use these real-time data, real-time measurements, and can then base our estimation for the economic potential on sound and real-world data. This has been the progress in the project so far. I thank you very much for your attention. And of course, we have a couple of minutes left for an open discussion. And also, I'm looking forward to your questions. Thank you.
Christian, can I ask you something? So I didn't understand quite well about the system is already quite flexible. Can you a bit more elaborate this issue?
Yes. What I mean with that is that the heat-only boilers itself can easily take care of the heat demand of the whole community. So one heat-only boiler in about, this is an estimate, I think about 80% of the time, one heat-only boiler would already be enough. And if we go up to the heat profile, two of the boilers together, the two boilers together are only really needed in times of extremely high heat demand. And if we only had one, then it would be necessary to cut the heat demand profile at a specific point here and shift it down to other points where the heat demand is potentially lower. And then what would be possible is to actually make a real cost reduction to the system. But right now, shifting loads does not really matter because the system is oversaturated with heat anyway, especially if we also introduce the hypothetical CHP and also heat pump. And therefore the cost reductions are very, very minor. Having said that, this is especially the case at this pilot site. There may be other communities where this is not the case at all. So the flexible buildings still have a very large potential of reducing the cost, reducing the peak loads. At this specific demo site, the cost reduction benefits are quite low.
So does it mean there is no need an additional CHP plant there in Mariala, actually, if the system is locally covered by heat demand covered by heat boilers?
Yes, the CHP and the heat pump are another matter. Both of them would potentially be financially very, very good for the community. The flexible buildings alone will probably not be, but the two new components will be, especially because you can make use of the dynamic day-ahead market prices. Also, if you use even a standard forecasting for day-ahead prices, you can kind of gauge when the high price situations will be. And if you do that, then the non-flexible buildings can be very much viable again, because, for instance, if you only can estimate good hours with very good prices, then you can potentially shift load from the load profile to hours of good prices. So for instance, here on the left side in the graphics, you can see that here we have a point of a very high price spike in the day-ahead market. So we do not want to buy here. But if the heat demand is very high at this specific time step, then we have to buy here. Using flexible buildings, it would be possible to shift the heat demand from here to a time of lower prices. So in conjunction with them, the flexible buildings would still make a financial sense. And also the introduction of new components are still financially viable if we are participating in the markets.
Thank you.
Yes.
Okay, hi. I don't think we have anyone guiding us who asks the next question, right? So we just go on.
Not really, okay. No. Just ask away, please.
Yes, thanks, Chris, for the very nice presentation. I have actually a couple of questions, and the first one can be on the slide where we look at now. Can you please explain, when we look at the figure to the right, flexible and inflexible, what is actual difference between these two? Because flexible is just overall higher than inflexible. So what is the reason for that? Okay, now you're muted, just in case.
Yeah, this is a very good question. For this question, I don't really have an answer because this is an excerpt that was provided to us by the demo site, which was an estimation of the heat demand. Yeah, it's a very good question, to be honest.
Yeah, but I hope I hope you see what I mean. I mean, the flexible, yeah, I assume, would be some hours higher, some hours lower, but it's overall higher. So I was just wondering what it means here. Yeah.
Yeah. So what we figured is that as I said, that there are major energy consumers and there are minor energy consumers, and the flexibility option is not available for all the housing objects in Maria-Laach, and therefore we have a bit of a larger part of the heat demand that can be shifted, and a smaller part of the heat demand that cannot be shifted.
Aha, so okay, so the part which is in red is the shiftable part.
Yes. So,
okay.
There's so this is what we figured, and we got this chart provided to us. Is that this is basically the baseline load. This is constant. No matter what we do, we don't have an automation system in place to even know how much heat demand this building has at a given time step. But when implementing the demo, there will be smart meters installed, or there are already smart meters installed. And using those smart meters, we can accurately measure the heat demand at a given building. And only those buildings, of course, can we use as flexible building storages.
Okay. And then I have another question, but I mean the new one, right to what you just said. When you were also saying before that using buildings as flexibility is economically viable, is this only based on the fact that, you know, when there is a price signal, the buildings react, and when there is no price signal, buildings do not react? But when saying that this is viable, do you include the investment cost in making buildings flexible?
No, not at all. So this is purely a physical model, and the only economic parameters that we used were the current market conditions. So a couple of things that were spared out of this simulation are, for instance, the cost for market access at all, because there's always a cost for that, which is, I guess it's paid annually, but I'm not quite sure. But the cost is still there, and it can be significant depending on what kind of market access you want. And of course, the installation of smart meters and also the whole automation system is also a potential cost factor that has to be considered. And this will be done on the basis of the pilot site data that will hopefully be available to us when the tests are finished. And on the basis of that, we are going to do the whole economic evaluation.
Okay, thanks. And then just probably a few smaller questions. I believe it was a previous slide where you showed some parameters for the CHP and heat pumps.
Mm-hmm.
And it was, okay, probably a bit more, somewhere here. I was wondering, what do you mean by binary operation? So it means that CHP plant can either produce 100 kilowatt or not produce anything.
Yes, exactly. So it's it's an on-off operation.
Okay. Because then, I mean, running some optimization models myself, I mean, that probably affects the solution quite a bit. If the CHP plant cannot produce 90 or 110, but only 100.
Yes.
That's. I'm just saying it's a bit unfair to the CHP and the heat pump that they cannot be flexible and heat-only boilers can be flexible.
Yes, this is true. This, on the one hand, the binary operation limits the potential cost reductions that the components can achieve. Yeah. On the other hand, doing the simulations with basically an omnipotent ideal vision of the market conditions, again, increases the cost reduction potential. One could argue how much both of these cancel each other out. The main reason for using the binary operation is that the exact parameters are just not well known to us, especially the efficiency curve, because the efficiency curves, as we can see at the optimization of the heat-only boilers, make a major difference. The only reason the cost reductions in increasing the efficiency are so small here is because the overall heat demand of 2,000 megawatt hours per year is small. But efficiency increase would make, it would make a much more complex model, of course. But you're right, of course.
Because I would just have an experience of still doing the binary operation, but in a way that the CHP plant can produce, for example, in between 100 and 40, let's say, the minimum bound. But then, between 0 and 40, it cannot produce anything. Basically, a binary or mixed integer optimization. But doing this thing, I mean, this is something new to me. So it's exciting, but also if you have any time in the future, try to, to allow the CHP plant to operate within some range, and then between 0 and the minimum range, still binary.
It would be very interesting. I just know from other projects the modeling of heat pumps it's usually done. I think it's binary from 0 to some kind of baseline heat output, and then you have a small scale where it scales with the efficiency, and so on. Yeah.
Yeah. And just the last comment from me. I mean, if you want to do in the future like some heat storages that are more centralized heat storages, my idea would be also, or just an advice, if you do have rolling horizon for 2 days, and if you have centralized heat, so it might be probably increase the horizon a bit, because the value of storage, which is a tank centralized one, on a daily basis, it's probably not so well represented if it is, for example, a week, because we can store heat for a week or a month, right? What I'm just saying is that the rolling horizon for only 2 days will probably do not show the whole potential of a centralized storage, which can store energy from week to week.
Yeah.
That's just a comment on this.
Yeah, it's a good comment. Thank you. Of course, limiting the horizon to 2 days also limits potential long-term storage options.
Yeah. That's a good short rephrasing of what I wanted to say.
Yeah. Thank you for your comment. Of course, it has been mainly a question of very boring pragmatic stuff like debugging and runtime.
But otherwise, thanks a lot for the presentation. Thank you.
Yeah, I'm glad. You're welcome. Thank you. Because we didn't have an introduction, are there any more questions?
Yes, I have one. I put my hand down now first. Thank you very much for your presentation. Very good discussion. Very interesting. Just the same slide that you're showing exactly. I had a question about the biomass price assumption that you have. It's relatively low. Is that is a local biomass that is used there, or is it? Do you think that will be the same values over time?
I will consult my colleague. Demet, could you help me out here with the data source?
I think Josef can help. Yes, he already switched.
Hello, everybody. This biomass price is the real price for the regional biomass that is used in the plant. It is an agricultural cooperative, and they produce the biomass, the wood chips, in a few kilometers surrounding.
And that was enough for, I mean, the availability in the region is enough to run CHP and the other, I mean, perhaps that would increase the cost if the number of this bio-CHP increases and so on. I don't know, but just thinking in terms of if there would be some policies that limits biomass use in heat, Austria, those type of things. It seems very relatively low compared to assumptions we make in Sweden.
Yeah, for the case in Austria, it is a good biomass price. Also, from the view of the forester. When you sell it on the free market, you will not get 30 euro per kilowatt hour. Maybe only the half. Yeah.
What is the price in Sweden of biomass? Do you know?
Yeah, the thing that I calculated quickly, just we talked together with Dima before this meeting. Those we have in our model, and it comes from some references that we talk about it can be about average, I can say 7 euro per gigajoule, something like that. When I divide this to 3.6 to get per gigajoule, it becomes much lower compared to our assumptions. But perhaps I don't know if you will look into the longer time period, you will have perhaps some assumptions on that, how biomass would change, the conditions for biomass, I mean. But thank you very much. It was very, very interesting.
Yeah, thank you very much. You're welcome. Another point from me, because you mentioned the biomass price. Of course, the data for this model is from the year of 2018, and I'm not entirely sure how the biomass prices have developed in the last 3 years, 4 years, 3 years. Do you know more about this?
Well, I can answer it. I think the market price of biomass were dropped in the last years because of this high calamities of the bug beetle and so on. But for the plant Maria Lach, it was the case because it's a cooperative. The prices are relatively stable, so they don't follow these market developments.
Okay, very interesting. Thank you.
Christian, I have one question to the modeling. As I followed right, the parameters were only the costs of the operation of the systems. Or is there also a factor from the investment?
There is no investment factor yet, no.
Okay.
This will be the whole economic potential, and also the additional investment factors and the market participation costs will be done after the first results are there from the demo site, okay, and also as part of the work package 5 of Flexi-Sync.
Okay, fine.
Yeah, good question. It's good to know.
Yeah, because I'm not was wondering, but I've seen the heat pump with 44 kilowatt and the biomass CHP. In both cases, we have to install a separate supply line from the electrical grid, because on site we now only have 30 kilowatt. So we can get 30 kilowatt from the grid and feed in 30 kilowatt. But with the planned CHP plant, we will have to make a new line to the grid. So this will be, of course, the case that we have to do.
Yeah, this has to be included in the economic factor, yes. Are there any more questions, comments? All right, then I just want to say thank you very much, especially for the discussion. It's always nice to have some questions in the end. If there are no further comments, I thank you all for participating. Maybe see you next time in the next webinar, and I wish you all a nice day, nice week. Bye.